In the case of non-ideal representation of the single phase transformer, which is on the left hand side of this, we see that we have few resistances and reactances, and we have discussed why do we have these components in the representation in our regular class. Now what we see is, if at all we wanted to bring all these impedances on the secondary side of the transformer to the primary side of the transformer, how they will be represented when we refer it to primary. That is, how do we represent this reactance when it is referred to primary, and how do we represent this resistance when we refer it to primary. Similarly, how do we represent this load impedance when we refer it to primary. So when we move all these resistance, inductance and impedance on the secondary side to the primary, the relationship will remain similar, that it is that ZL dash, which is referred to primary of the transformer, is going to be A square times of ZL. Similarly, our R2 dash is going to be A square times of R2, and our X2 dash is going to be A square times of X2. Similar to that, when we have our voltage on the secondary side, that is V2, when it is referred to the primary side, which will be V2 dash, is going to be A times of our V2. And we know that the voltages and currents are inversely related, so our I2 dash is going to be I2 divided by A. So this is how we will be able to move all the resistance, reactance and impedance on the secondary side of the transformer to the primary, and they are represented with this terminology. Right? So and now this is again like a simple RL circuit. Just the numbers will be changed on the circuit according to the turns ratio of the transformer. Let us say we have the value of our voltage V2, which is also taken as a reference. Now if we know the value of V2, then let us see how do we calculate the values of the voltages and currents at various parts of this particular network, and also how do we calculate the value of voltage V1 in this equivalent circuit. Now instead of solving the network using this equivalent, we prefer to solve our network using this particular equivalent. So in this particular equivalent, if you already know the value of V2 at an angle of 0, that is actually the value of V2, then your V2 dash is just A times of V2 at an angle of 0. Now, if you know the value of V2 dash, that have a look at it, if you know the value of V2 dash, then the current flowing through this particular branch, which is same as the value of I2 dash, can be calculated as, we can write down the value of I2 dash is V2 dash upon the value of ZL dash. That's what we get from our second equivalent circuit. But if you already know the value of I2, then you can also write down that as I2 upon the value of A. So these are all your vectors that we have been calculating because they are associated with the complex numbers. Now provided you have your I2 dash and V2 dash, now have a look at it. In this equivalent circuit, you know the value of V2 dash, and you also know the value of I2 dash that is flowing in this branch. Then you will be able to get the voltage at this particular point as the sum of the V2 plus the drop across this R and L. So now voltage at this particular point, we are also saying it as E1. So I can write down my value of E1. If you would like to call it as a vector, you can call all these values as vectors. Now E1 is how much? It is V2 dash, which is a vector, plus we have the drop across the resistance and reactance. That is, you have your I2 dash is a vector multiplied by R2 dash plus J X2 dash. This will give us the value of your E1. Now, E1 is nothing but the voltage across these points. Now that voltage can be divided with the resistance or the particular reactance in order to get the values of IC as well as IM. We can say that if you wanted to know the value of your IC, that is the current corresponding to the core losses, that is E1 upon RC, that is your IC. Now similarly, if you want to know what is the value of our IM, which is E1 upon JXM, it's also a vector. Now if you add these two currents, that is when you will get the current that corresponds to no load, which is IC plus IM. Now after knowing the values of I no load, we also know the value of I2 dash. Now you see at this particular node, this is where you see that the I no load is going down and then I2 dash is going up. So this is your I2 dash, this is your I no load. So the amount of current that is coming into this particular point is nothing but our I1, which indicates that the value of I1 can be calculated as I2 dash plus I no load. Now once you have the value of I1 from this particular equation, that is when you can calculate your V1 as E1 plus your I1, the corresponding drop that exists in this network when the current of I1 dash is flowing is R1 plus J XL1. This will give us the value of voltage on the primary side. That means if you have seen a voltage of V2 on the secondary side of this particular transformer, then that will be due to V1 voltage on the primary side of the transformer. So how do we get this V1 from the value of V2, which is taken as a reference? This is how we'll be calculating it. So how we are getting the value of our V1, provided that we know the value of V2 and it is taken as a reference, are summarized in this particular steps. So another important thing here in the non-ideal representation of the single phase transformer is what are the losses and how do we get to know the efficiency of a transformer. So now we see that the lossy component in the equivalent circuit is due to the copper losses on the primary winding of the transformer and then copper losses on the secondary winding of the transformer, and then there is also a resistance or lossy component that indicates the core losses in the transformer. So the copper losses, that is copper related losses on the primary of the transformer, are related to the resistance R1. So we can write down that as I1 square multiplied by resistance R1. Similarly, we also have the copper losses on the secondary winding of the transformer, that is P copper losses on the secondary side of the transformer is nothing but I2 square times of the resistance on the secondary is R2. And as well as we also have the core losses which are due to the current IC, that is a leakage current due to the core, and the resistive representation of the core, which will be IC square multiplied by R C. These are basically core losses. So now when we add the total losses of this particular transformer, that is power losses in the transformer are due to copper losses on the primary and copper losses on the secondary as well as the core losses. And now these are the losses, and if you want to know what is the efficiency of the transformer, that is output of the transformer divided by the output that we have plus losses. And you can also write it as our output upon input if we have the information about the input power that we are giving and information about the output power that we are getting from this particular transformer.